UGP Paper 1, May 2022. Question 1. Which row contains vector quantities? So acceleration is a vector, has direction and size. Mass is a scalar, so this is not correct. Part B, it's displacement. Displacement is a vector, is a distance, direct distance between 2 points in a given direction. And momentum is a vector as well. So the answer is B. Let's just double check. C, energy is a scalar, distance also a scalar, speed is scalar. So we're looking only for vectors, and therefore the answer is B only. Question 2. It says, which component is an ohmic conductor with the greatest resistance? So we're looking for two things. It's an ohmic conductor, so that means it obeys Ohm's law. That means that the potential difference is directly proportional to the current. Okay, so that means that the proportion in which the voltage goes up in, it's the same proportion as which the current goes up in. So if you have a look here, the voltage is jumping by 2, 4, 6, 8, 10, 12. So the current should jump in equal jumps as well. So that's 0 to 0, 0 to 0.1. That's not equal jumps. And again, because that's not an equal jump from there to there, that does not obey Ohm's law. B, you've got 0 to 0.3, that's add 0.3, and that's add 0.3 again, add 0.3, add 0.3, add 0.3, add 0.3. So that there, it's jumping in equal portions from 0 volts to 12 volts. And C also does that as well. So 0.0 to 0.4, that's a jump of 0.4, and that's the same jump each time. So there's a possibility between B and C. D, you got jump in 0.3, 0.3, 0.3, then a jump in 0.2, 0.2, 0.1. So D is not jumping in the same proportion. So therefore D is out of the question. So now what we could do is the greatest resistance. We know resistance is voltage divided by current. So just pick any. So the voltage is 12 divided by 1.8. That gives you a resistance of 6.67 ohms. And 12 divided by 2.4, that gives a resistance of 5 ohms. So the one that has the greatest resistance is B. It is an ohmic conductor. It shows direct proportion between the voltages and current, and it has the greatest resistance. Question 3. A perfectly elastic rubber ball falls vertically from rest. Okay, so we'll look at this statement shortly, but when it starts from rest, it means it starts off at zero speed, zero velocity. So part C is out of the question straight away because it starts off with a finite velocity. So that's wrong. And rebounds from the floor and moves back up. Now, so what we've got is we know that when a ball falls, it increases in speed. So we can see in A, we've got an increase in speed, and in D, we also have an increase in speed. Okay, when it hits the floor, what happens is the ball slows down. Okay, and rebounds up. So when it slows down, what happens? It slows down to zero speed upon impact, and then increases speed in the opposite direction. Okay, so what we are looking at is for an increase in speed when it leaves the surface. Okay, so and then at the top of the bounce, it is zero speed. Now, velocity is a vector, so what we are looking for, the thing that distinguishes D from A and B, is that when the ball is moving upwards, it has a negative velocity. When it's moving downwards, it has a positive velocity. Now, that shows that the ball has changed direction. Neither A or B show that. And also, as the ball is falling, the gradient is constant and fall is under the force of gravity. So 9.81 is the acceleration, and that's the gradient, and that's the gradient in both scenarios, and the gradient is 9.81. Now, in reality, we should draw it like this because we know that when a ball falls downward is a negative direction, a negative value, and then upwards, when it's moving upwards, it is a positive value. So often you'll see it in reverse order. In this scenario, um, the key thing is identifying the change in direction and the change in value of the velocity. Question 4. Resistors X and Y are connected in series with 6-volt battery of negligible internal resistance. X has a resistance R, so I'll put that next. The resistance of X is R. The resistance of Y is R over 2, so R over 2. The voltmeter of resistance R is connected across Y. So there's a voltmeter connected across Y, but it also has some resistance. Now, we normally have voltmeters when they work. We assume they have infinite resistance, but this question has said it has resistance. So think of it as another component in the circuit. Um, so it's this is then becomes like a parallel arrangement of resistors because a voltmeter is actually with a finite resistance. So what we are looking for is the voltmeter read. What is the voltmeter reading? Now, one of the most straightforward ways is look at this and find the resistance in the parallel section. So reduce this to one resistor. Okay, so how we do this is 1 over the resistance here plus the 1 over the resistance here, which is R, and that will give you 2 over R plus 1 over R, and that's 3 over R, and we have to flip it to get the total resistance of these two components, which is R over 3. So what we're assuming is this here acts as a single resistor of R over 3. Now, so there's your X and there's your Y. Now, we know that when we have this arrangement, it's a series arrangement, the voltage of 6 volts splits according to the proportion of these resistances. Okay, so now what we can do is we can look at ratios. We can say that this is 3 times bigger than that. So the voltage here should be 3 times bigger. The voltage at X should be 3 times bigger than that of Y. So straightforward ratios will reveal the answer, but also you can use the potential divider equation. V out is V in over R1 plus R1 plus R2. 6 is the input voltage. We're looking for the voltage across Y, which is R1 there, therefore becomes R over 3. And then the total resistance is the resistance R plus the resistance R over 3. And we get R over 3 divided by 4 over R over 3. They cancel out, and what we get is 6 times a quarter, which is 1.5 volts. So if this is 1.5 volts, then that means this is 4.5 volts, which makes sense. So we know that this is 3 times bigger than that. So the voltage here will be 3 times bigger than that, which it is. 4.5 volts is 3 times bigger than 1.5 volts. So therefore, the voltmeter should read 1.5 volts there. Question 5. The drag force on a boat is kV squared. So this is just given to you. Where V is the speed and K is some constant, 64 kilograms per meter. The boat's engine has a useful power output of 8,000 watts. So this is what the engine is producing as acceleration. The rest is obviously wasted as heat. What is the maximum speed of the boat? Okay, so when we have maximum speed of any vehicle, the net force is zero, so it can't accelerate anymore. Okay, so the acceleration is zero. That's when we reach top speed. So the overall force, net force, is zero. That means that at that moment the drag is equal to the forward force. Okay, so we know an expression already for drag, which is kv squared, and then that becomes your driving force as well, which is that there. Okay, now we know also that the power is linked to force by power equals force times velocity. So we know that the force, the driving force, is the thrust, and we know that's equal to the drag. So it'll be the thrust multiplied by speed. So we're looking at the maximum speed. Um, so V, when we reach top speed, they'll stay at top speed. So that is a constant value. And then we know that the thrust is equal to kv squared times by speed, which is V. That's the same V that we are looking for. And that'll be kv cubed and equal to the power. We've got the power, we've got K. So all we do is rearrange, and we cube root power over k, which is 8,000 over 64. That's 125. Root that, a cube root that, and that's 5 meters per second. Okay. Question 6. A resistor with resistance R is made up of a metal wire resistivity rho. The length of the wire is L. So we know that R, a resistance, is linked to resistivity by this formula, R equals rho L over A. We want to look for what's the diameter, but the diameter will be embedded in the cross-sectional area. Okay, so we are making the assumption that it's a cylinder, and as soon as it says diameter, we're assuming it's a cylinder. So the cross-sectional area is pi r squared. They want it in terms of diameter, so we know that diameter divided by 2 is the radius. And when we multiply all of this up, we get pi times diameter squared over 4. And all I've done is now substitute that into area, put the flip it so that the 4 is at the top, and then that's pi d squared at the bottom. Then we want to get what the diameter is, so we need to make diameter the subject. So diameter squared, just swap r with d squared. That's a quick trick. So it's 4 rho L over pi r. Root that to get rid of the square, and we get this expression here. And we look for that expression there, but there is no 4. They've pulled the 4 out. So if we pull the 4 out of here, it's root that the same. That's the same as 2 root rho L over pi r, and that is that here. Question 6, the answer will be C. So question 7, it says an object is in equilibrium. So that means that the net force is 0 and there are 3 forces acting on it. This is a free body diagram that you see below, a set of free body diagrams. And it says that these diagrams are drawn to scale. So that's important as well. So the first one, I'm going to look at these forces. So an object, let's say, is placed right there. There's your object, right in this position here. And there is an upward force on it, a force to the right, and a force diagonally down this way. Now we can easily see that these two forces are 90 degrees. So we know that the resultant force of these two, using the parallelogram technique, is going to be somewhere here. Because it's drawn to scale, we can mimic the size of the result of these two here, okay, which is going to be that there. And as we see, the direction of this force and the size of this force arrow is directly opposite and more or less the same size as this arrow here. So that force cancels out that force. So that means that the net force is equal to 0, which satisfies the condition of equilibrium. Another way to do this is start off with one of the forces, draw it out, then where that arrow ends, pick another force, pick that one and draw that to scale. And then where that arrow ends, draw the next one back in the direction it is, the same size, same angle, and you'll see that it should end up in the starting point if the condition of equilibrium is met. So when you do a head to tail, if all the forces with the head to tail force diagram end up back at the same position, that means that the net force is zero. So that means that's the answer. But let's check the others and see why they are wrong. So these two forces here act against this force here. And what I could do is I can do a quick parallelogram for these two forces. So there's my parallelogram, and the resultant force is that there of these two forces. And we can see that although this force is opposite to this, the size of this arrow is not equal to the size of this arrow, so you're not going to get a net force of zero here. Okay, so that's why B is wrong. And C, the net force of these two here, and pick these because they're 90 degrees, is going to be approximately this way. And this force is not in the opposite direction, in this direction, to cancel this out to get a net force of zero. And these two forces, the net force is in this direction, and that's the same direction as this force. So the overall force compounded will be in this direction. So therefore, there will be no net force, not there will not be a zero net force in part D as well. So part A is the only plausible answer. Question 8. So we got two cylindrical wires, P and Q, equal length and same material. Okay, same material, that means same resistivity. The diameter of P is greater than the diameter of Q, so the cross-sectional area is a variable here. So they're connected in series and connected to a power supply. So what I've done is I've just kind of said, oh, okay, there's our circuit. I've drawn a power supply here, and we've got that. Okay, now it says which two quantities are the same. So let's look at each one separately. Now, we know that resistance is equal to rho times by L over A. We've been told that the resistivity is the same because same material, same length. So we know the cross-sectional area is different due to the diameter being different. So that means the resistance is inversely proportional to the area. So because this is a series circuit and P is going to have its resistance and Q is going to have its own resistance because they have different cross-sectional area, that means that the voltage that is provided by the power supply is going to be shared, well, not equally because the resistances are not equal. Okay, so the potential difference across each of P and Q is going to be different because the resistances are different, and the ratio of resistances is going to be different across each. So therefore, the output voltage at each point is going to be different. So that's not it. Resistivity, we know, yep, same material, that is the same. So both of the quantities have to be the same. Resistivity, we know, yep, same material, so they have same resistivity. And because it's a series circuit, the current throughout this entire circuit is also going to be the same. So B is the answer. But carry on, let's carry on, check why the others aren't. Current is the same because it's a series circuit. Resistance is not the same because the cross-sectional area is different across each wire. And we just said that resistance is inversely proportional to cross-sectional area, providing that the other two are constant, which they are. And the cross-sectional area is different, therefore resistance is different across each of the each PQ. Resistance, as we just said, and potential difference earlier on, we said that's not the same because the ratio of resistance is different. So therefore, B is the answer. Right. So an electric motor is it's lifting an object and through a vertical height h, and it takes some time t to lift that object, a height h, and the potential difference across the motor is V and the current is I. So efficiency, we know, is the useful energy divided by the input energy. Now, I've gone with energy because I'll go with energy first, and if power is the right way, then I'll do power. But useful energy over input energy. So the input energy is from the motor, and that's power multiplied by time. Okay. Um, Now, I've just left it as that. We'll leave it as that. And the useful energy is we're lifting the motor vertically up. So the useful energy is GPE. So it's mass times gravity times height. Now I'm looking for something like this because the useful energy is the gain in GPE. That's why I've gone down the route of MGH, and then that means the input energy. I could write E, but because I'm looking at the voltage and current and that's linked to power, then there'll be power times time. I'm going to look for this answer and I can't see power. So they've expressed it as voltage times current. So we know P equals I times V. So that means P is I times V. So I times V is the power multiplied by the time. It's the input energy from the motor. Now, let's have a look for IVT, 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 IVT. Well, the only one with IVT at the bottom, and that's that there. But they don't have MGH, but we know that MG is the weight. So as we say it as your weight W. So what we've done is we've replaced mg with W. So W times height is the useful energy, which is the gain in GPE, and IVT is the input energy from the motor, which is power multiplied by time. So question 10, one of the first thing I recognize is I've got a current coming in here to a junction there and a current coming in here to a junction there. Now we know that when current joins up at a junction, we know that it will add up. So this current incoming, incoming, so these two add up to give you 6 amps going this way. That's the first point to answer this question. Now we were looking at the potential difference between this point and the earthing point here. So we know that the current going through this resistor, um, and we know the resistance. So with current and resistance, I can find potential difference. So the potential difference across the 10 ohm resistor is 2 times by 10, which is 20 volts. And the potential difference across this resistor is 6 times 20, which is 120 volts. These two components are in series. So the potential differences add up. And we're looking at potential difference between this point and this point. So because these two are in series, we add the potential differences up, and that's 140 volts between P and the earthing point. Okay, so that's the how you work out this answer here of 140 volts. These two are in series. We know the voltages as we've calculated them, and we know that voltages add in series. Okay.